So now we're going to get into organic synthesis. And just to give you a heads up, there's a difference between mechanisms that we've been using the curved arrows for and reaction descriptions for a synthesis itself. Now, the mechanisms will tell you and enable you to predict what's going to happen. But when you write a synthetic sequence of reactions, you don't use curved arrows. You only use what's available in the lab that goes into the reaction itself. So you include spectators as well. Remember, mechanisms, we left spectators out. Okay. That's not supposed to happen. Oh, I know. Okay. It's part of my animation. I fooled myself to begin with. Okay, I already said that. We've been working with mechanisms so far. And those ends need to be subscripted. Missed that one. Okay. Designing a synthesis, and we're going to look at later on in subsequent chapters, we're going to look at methods for designing a synthesis. And a synthesis itself has a target in mind. In other words, you want to end up with a particular molecule. So you design the steps to get you there. That's the synthesis design. All right, this is just an outline of where we're headed. So I'm going to I've still included outlines. So we've got 9 sections in this chapter, 10, 12 sections. All right, so this is the general outline of a synthesis, and it can be more than one reaction in from the starting materials to the synthetic target. In this case, we have 3 reactions, and the A's and the B's are intermediates. So you have the starting materials, and the starting material should be something that's available commercially. Or you can derive them from natural sources, which is often the case with drug development. We'll take natural source precursors and just modify them slightly to our own ends, rather than working from the simplest inorganic compounds. Because very often organic reactions are very inefficient at duplicating the production of certain types of substrates. And whereas natural products with their are created by enzyme systems that are specifically designed to produce those starting materials. Good starting materials tend to be low cost. You don't want to start with very expensive stuff because you're going to put a lot of effort into it, and that's going to add to the cost anyway. And they should be safe materials, as safe as you can get them. Not only safe for you in the reaction environment, but if they're natural sources, you want them to be obtained safely. In other words, you don't want some company to rape the natural environment just to get your products. Okay, now we can proceed to the different steps of the synthesis. Each one of these is called a synthetic step, of course. And the A's and the A and the B in that setup there are considered intermediates. They're not the end product, but they're on the way to your target. Okay, so now we're going to talk about conventions. This is like the syntax of your language. In order to communicate with other chemists, we need to agree upon certain types of presentations. And in this chemical reaction, we want to set it up so that we can have now for this one, that's only one step. Right? This example is only one step. Right? You can do this for multiple steps, but you want to have just the overall reactants, anything that goes into the reaction environment, any reagents that are added, reaction conditions can be specified. In fact, they should be specified, and then the overall products. So in this particular case, we know that we've got a good starting material if we're going to do a substitution because we have a good leaving group. That tosylate moiety there is a very good leaving group. It'll be easily substituted with a bromine. You shouldn't include any details of the mechanism, not for a synthetic procedure. So if we were to take that particular reaction and break it into its mechanisms, then we would have multiple steps, and it would look radically different. In other words, this would be the leaving group would leave first for this SN1 reaction, and that we classify that as a heterolysis. We just break the bond, and the electrons go to the tosylate ion, and then the bromine attacks. That's a coordination, and we end up with a product. So when we write the mechanism, it looks radically different than the synthetic step. If we're going to write a synthetic step, we want to have the reagents of any kind listed as they would appear on the shelf. You pull them off the shelf, that's what they look like. So when we say the bromine ion is going to react with this molecule, that's not a synthetic step because you don't go to your shelf in the laboratory and pull off bromine ions. They always have countercations. So it would be maybe potassium bromide or sodium bromide would be the reagent that you'd be using. The second one is an example where we have hydroxide. Now we know the hydroxide would be a relatively good base, but what form would it take on your chemical shelf? It would also have a counter ion like potassium bromide or sodium bromide, lithium, potassium hydroxide or sodium hydroxide. All right, so those would not be very good steps. We would have this example where the hydroxide is listed for our synthetic step as sodium hydroxide. The second convention, so first convention is you want, maybe I ought to write those up here, keep myself straight as well. Convention of synthetic steps. Okay, so the first convention is write, learning, write reagents as they as they are found. In other words, we don't write ions in there as standalone because they don't exist that way. Second convention. I'm writing synthetic steps. The all the reagents, and the reagents could be reactants as well. The reagents could be solvents, they could be reactants, or they could be just there to establish the reaction environment. But those have to be written somewhere. And usually they're written on the arrow. So this, we want this iodide ion there because it's going to be the nucleophile. And we're going to write it on the arrow. And then we write the conditions there as well. This is dissolved in acetone. It's an aprotic solvent. And we're going to conduct this experiment at 40 degrees Celsius for 3 days. Those are reaction conditions. Now, whether you place them above or below the arrow is a point of personal preference. Many chemists put the reagents above and the conditions below. But when you get to the point where you're going to have multiple steps, and I'll show you that in, I think it's convention 3, and you number the steps as sequential, then that's kind of hard to do. But if it's a single step, then you could write the reagents above and the conditions below. That's an open item. Okay, here's an example where the solvent is also a reagent, and you don't write it twice. We got a fancy name for that called solvolysis. The solvent is also a reagent, and we don't write it as the reagent is methanol, and then we write it again as the reagent is the solvent. I mean, it's in there, it's in the reaction environment, and we just have to recognize it as both the solvent and the reagent. Convention 3. These are multiple steps. Use numbers to combine reactions in sequence. Let's see, I left, what was number 2? Number 2 was reagent and conditions. On the arrow. And 3 is sequential steps. Are numbered. So what we're saying by numbering these steps, we're saying the first reaction we're going to conduct here is the sodium hydride with a pent-1 ion. And then after we've allowed that to react to a certain point, it produces some intermediate. And then we're going to react that intermediate with the methyl iodide. And that produces the end product. So these are sequential steps. Sometimes it's done for convenience. Sometimes it's done for the fact that separate it from the reaction environment is difficult or impossible. So you just conduct the reaction in steps. In this case, we have 1-bromohexane, and the first step has the let's see, butoxy anion is what you're after here with this potassium salto-butoxy anion, but it's in an aprotic solvent, DMSO. So that reaction has to be conducted aprotically. And then the second step, once you produce that intermediate, the second step, you add bromine and then water. Now you've got a protic environment. You're changing the aprotic to the protic. And that produces the final product. Now, when you have multiple steps like this, it's usually convenient to use a a comma, separate the reagent from the conditions. So I can imagine under some reaction conditions, you'd have an arrow that's this long, or either that or you'd have to stack them. Okay. Um, okay. For each of the reactions that you encounter, you have to ask yourself these following questions. What functional groups or reactants are involved? Remember, we're introducing this topic of organic synthesis in terms of functional groups first. We're going to get into modifying the carbon chain. Functional group reactions are much easier to conduct, and for the longest time, that was a sticking point in organic chemistry, historically speaking. The modification of the carbon chain difficult. You couldn't make it longer. You couldn't turn it into a cycle easily until the the discipline matured. But functional groups came first. You can modify functional groups fairly easily and control the outcome. And we're going to talk about that extensively here in just a few minutes. So what functional groups are in the reactants? What functional groups are involved in this reaction? And then what functional groups are produced in the products? You start off with functional groups. Maybe you're going to modify them. Maybe you're going to eliminate the functional group from the reactant and substitute some other functional group for it. And when we say functional groups, that covers individual atoms too. But you can substitute groups or you can substitute atoms in this reaction. Or you can change the functional group from some appendage to a pi bond, if it's an elimination reaction. And then you look at the major structural changes that occur. Now, this can be carried over into the establishing carbon-carbon bonds. But right now, we're talking about structural changes that involve non-carbon changes. But this can also be ported over to subsequent chapters where we're going to discuss modifying carbon chains. All right. So in each one of your chapters, you're going to have these tables. And I've printed out the one printout I've got over there that looks like tables has chapters. I think I've got 9, 10, 11, and 21 in there in that one document. So they're all together. This is an example from chapter 9, which, well, I stand corrected. We have altered the carbon chain already. Oh, we altered carbon chains in mechanisms. We haven't talked about altering carbon chain, carbon skeleton yet in terms of synthetic steps. Okay, so we're going to get to that eventually. So these tables summarize, and they're all going to be in the same format. In other words, the first thing in that row is going to be starting compound, whatever class it is. In this case, our example here is an alkyne. And then it's going to have a two-step reaction with sodium hydride and a halogenated alkyl group. And then we're going to in that two-step process, we're going to tack on that alkyl group to the alkyne. And then we identify what are the electron-rich and what are the electron-poor species. And we call them electron-rich and electron-poor simply because they could be considered nucleophiles in certain reactions and bases in other reactions. And then in comments, we're going to say what type of reaction are we proposing with this particular change. And then lastly, where is it discussed in the text? All right. So I should have clicked on that and put the rest of it up there. But that describes, and this format for our reaction tables is going to be the same. And those reaction tables, since your exams are open book, you can reference those tables anytime you want. All right. Let's see. So here we have a sequence, a synthetic sequence, and our starting material is hex-1-ene, and our end product is 2-ethylhexane nitrile. So how do we get them? Well, let's see. We're starting off with 1, 2, 3, 4, 5, 6, 6 carbon chain. We're going to end up with a 1, 2, 3, 4, 5, 6, a 7 carbon chain with a change in the functional group as well. And we go through these different steps. Let's see. Yeah. We can have 2 table types at the end of each chapter. They're separated for clarity. One table will describe functional group transformations, and the other table will describe functional group conversions that do not alter the carbon skeleton. And then that was the first table. Second table are the carbon skeleton transformations. You're going to change the carbon skeleton in some way. And we've done both in this sequence of reactions, because we started off with 6 carbons in our chain. We ended up with 7, plus we changed the functional group. And that's just a sample. We have, and in this case, we haven't gotten to all those possibilities yet, right? Because I've identified the intermediates according to the chapter they occur. The D at the very end, we've covered that one, right? That's chapter 9. Then chapter 10 is right now we're in that one, and we haven't got to that yet. And then chapters 11 and 13 will cover those other transformations. Okay, so here's a functional group transformation, and we see it's laid out the same as described before. Sometimes you can accomplish the reaction with multiple elementary steps. SN2 reaction for the first one, and SN1, SN2 for the second one. Okay, so let's start with this Williamson ether synthesis. And I assume it's named after whoever proposed it first and accomplished it. We're going to make an ether. And in order to make this ether, yeah, that's right. In order to make this ether, we have a starting material, 1-bromobutane, and then we have a reagent, which is the 1, 2, 3, 4, the butoxy anion. But since we're describing a synthesis, we have to include the counter ion, the sodium. This is the sodium alkoxy. But notice that it's got the same number of carbons as the 1-bromobutane. So this is going to produce a symmetrical ether. Right? This is a dibutyl ether, but when we name it, I'm not sure why they're going to say dibutyl, because if we say it's a butyl ether, that flies in the face of my correction of one of the problems in our in one of our quizzes, right? Symmetricals, you don't have to say di. You say butyl ether, and it's on both sides. So that needs to be corrected. But the proper IUPAC name is 1-butoxybutane. All right, so the mechanism is shown below. What happens? Well, the nucleophile is the butoxy anion, and it attacks the carbon to which the leaving group is attached, forms a bond with that carbon, and now we have 4 carbons on one side of the ether and 4 carbons on the other side of the ether. And this is a one-step process with an SN2 reaction. This is known as a condensation. And what we didn't include, let me back up. What we didn't include in that synthesis was reaction conditions. These reaction conditions are acidic with heat. Now, you're going to encounter condensation reactions all over the place. And condensation reactions happen quite commonly in biochemical situations. And when they do, in the biochemistry, condensation reactions typically eliminate water. But in organic chemistry, we only need to eliminate a small molecule of some kind. And usually it's water, but it could be something else. Whereas in biochemical situations, it's nearly always water. When you form a true fat, you esterify glycerol with a fatty acid, it always eliminates water. Okay, so this condensation reaction produces a very high yield of the butyl ether. And just as an interesting fact, natural fermentation of sugars will produce the butane 1-ol in small amounts. So we have a natural source of butane 1-ol for our reaction. And it's often used as a flavoring agent in some foods, especially ice creams. Not the ether, but the alcohol. Okay, so what's the mechanism if, hold on a second, let me back up. One bromobutane, okay. All right. You didn't catch me, did you? Or were you just thinking? He thinks they're the same reaction. They're different reactions. Right? That first reaction is an SN2 reaction with a bromine as a leaving group. With the second one, we're going to produce a condensation product where we're starting with an alcohol, and we've got these two alcohols in this condensation reaction, and the butyl ether is produced by one butane 1-ol being attached to the other butane 1-ol in acidic conditions. Now, this is the mechanism where that occurs. First of all, hydroxide is not a good leaving group. So we have to convert it to a good leaving group. That's why acidic conditions are necessary. So the acidic conditions transfer a proton to the hydroxyl and make it, the leaving group now is water. While it's still attached, it's positive. But the SN2 reaction now can occur when the hydroxyl, the butanol, is the nucleophile, and it attacks the carbon so that the water molecule can make a neutral ether. So we need another proton transfer. So in this case, okay, I'm getting a message. Temporary. I got a message says it was unstable internet connection. But I'm hardwired, so it shouldn't be that bad. So we get a proton transfer followed by an SN2 and then another proton transfer. And we end up with the same product, but by a different mechanism. This is a condensation mechanism. Okay. All right. Normally, we would expect, since the hydroxyl is Well, the nucleophile is supposedly very weak, right? The sulfuric acid is weak. Um, well, I'll take that back. Okay. The proton transfer makes a good leaving group, but the attack by the other butanol is a weak nucleophile, and it occurs in a protic solvent. So we would expect an SN1 reaction. The problem with that is if we get an SN1 reaction, that water would have to leave behind a primary carbocation, which is unstable, which means that SN1 is not feasible. So we're left with an SN2 reaction to obtain the ether. Now, I would add that if we have, rather than a primary alcohol, we have a secondary alcohol, then the SN1 reaction becomes possible because it would produce a secondary carbocation, which is much more stable. So that's one of the caveats for this condensation reaction is where is the OH located? Is it primary or is it secondary? Okay. So there's a limitation to this condensation reaction to produce ethers. And that is that you cannot produce unsymmetrical ethers by this reaction. Here's what would happen if you tried to do that reaction with a a propane 1-ol and a propane 2-ol. So we used to say the first one was in red. The first one is normal propanol, and the second one is isopropanol. But the new terminology requires 1-ol and 2-ol. If you try a condensation reaction with this one, you're going to get a mixture of products. In other words, you could condense the propane 1-ol with itself and produce a symmetrical product. Or you could produce the propane 2-ol with itself and produce a symmetrical product. But you could also produce the desired product, the 1,1-methylethoxypropane or isopropyl propyl ether. You could produce that one. But you're going to get all three of those products with this condensation reaction. Now, if you don't care, then go ahead and do it. Right? And if you have to separate it, then good luck. But we'd rather, if we only want the asymmetrical ether, we need to use a different method. Right? So in order to get the asymmetrical ether, we're going to go back to the one of the reactants is going to have the leading group on it, right? The 1-iodopropane. And the other is going to be the attacking group. The where we had used in the past, in the previous slide, we used the propane 2-ol. Now we're going to use the propane 2-oxy anion. And that means that it will only attack the alpha carbon of the 1-iodopropane, and the iodine will leave. And now we get our asymmetrical ether. And this is an example where the Williamson ether synthesis that we saw at the very beginning can produce either symmetric or asymmetric ethers. We just need to start with, if we wanted to, how would we produce a symmetrical ether from this one? Well, we would have an alkoxy anion that's the same carbon skeleton as the 1-iodopropane. And then the attack would produce it would be a primary alcohol, would produce the desired symmetrical ether. But if we do it this way, we can get an asymmetrical ether. Okay. Now, Williamson ether synthesis does have its limitation. And this limitation is due to steric hindrance. If we try to attack that, the carbon to which the leaving group is attached, so that we can form the ether, we're not going to get the ether by an SN2 reaction because of steric hindrance. That oxygen can't attack that carbon because it's got a 3-methyl group sticking out there. They're in the way. So what you actually get is an E2 product because it can't attack the carbon. Now it has to attack a hydrogen. And when it removes the hydrogen, now we get an E2, the bromine leaves, and we get instead a pi bond. So if you try to do the Williamson's ether synthesis this way, you're not going to get the desired product. You're going to get a propene instead. And it's all based upon steric hindrance. All right. So this is asking us, how would we use Williamson ether synthesis to produce the ether shown? Right. We know we can't do it by this particular procedure. So how would we get there? Well, suppose instead of having the ethoxy anion as our attacking group, suppose we put the oxygen where the bromine is and put the bromine where the oxygen is. Just reverse them. Now the attacking group doesn't have problem with the steric hindrance. And the oxygen sticking out there, it can attack the carbon to which the bromine is attached, and we can form the ether. Okay? So that's what we're going to do. So down there at the bottom, you see, now we have the oxygen is attached to the tertiary carbon, and the bromine is attached to the primary carbon on the ethyl, the alkyl ethyl group. And now we can get the product we want. All we had to do was switch places with the bromine and the oxygen. Okay. So suppose we want to end up with this particular ether, right? Where we've got a benzyl group on one side and a cyclopentane on the other side. So it's definitely unsymmetric. And but remember what I said at first. You need things that you can get off of your shelf, right? You want the chemicals you start with to be stable over long periods of time. So if we're starting off with alcohols on our shelf, right, which would be what? A benzyl alcohol and a cyclopentyl alcohol. Then how would we convert those into these reactants so that we get the ether we want? Right? We've got to take the benzyl alcohol and convert it into a chloride, and we've got to take the cyclopentyl alcohol and convert it into a alkoxy. Okay, so that requires functional group transformations. Okay, and we can produce each one of those from their starting materials, they're alcohols. And this would be included in our synthetic steps, right? We would have to tell, it's like a recipe, right? If you want somebody to take your recipe and produce the product or produce the cake, you got to tell them every step. So we would have to tell them the transformation steps also on the way to producing our asymmetrical ether. And this, it would be fairly simple, right? All we need is the acid of the halogen, and we could convert that alcohol into an alkyl halide. And then for the other one, we could convert that one, since we want that one to be the attacking species, the cyclopentanol. Then we would just treat it with sodium hydride, and that would remove the hydrogen and produce an alkoxy salt with the sodium, right? So what's another product that we're going to get out of this? We're going to get hydrogen gas, right? that hydrogen from the sodium hydride is going to attack the hydrogen, remove the hydrogen, proton transfer, and produce hydrogen gas. So you probably want to conduct this preparation under a fume hood. All right. So the final synthesis would be converting one alcohol, the benzyl alcohol, into the chloride, and then we would have a separate stream feeding in with the cyclopentyl alcohol to its alkoxy, and then we could produce our product. So that would be a representation of the final synthesis, although we haven't included conditions here. So I think this synthesis is incomplete. Excuse me. So if we're going to convert an alcohol into a halide, the mechanism tells us why we did that in the first place. We did that because the alcohol is a very poor leaving group, right? And we would prefer bromide as our leaving group. So we're going to add heat for 4 hours, concentrated hydrobromic acid, and that will give us our brominated starting material. We need a proton transfer and SN2 reaction to get there. That's the mechanism. Okay. But as our molecules become more complex, the potential for unwanted side reactions is always present. And that's been the bane of organic chemistry from its beginning, is side reactions. And that's why one of the reasons, well, I think it's the primary reason that cells use enzymes as catalysts, because the reaction won't go efficiently without the catalyst. And then if you pick the enzyme as your catalyst, it is extremely specific for the outcome. I mean, it's stereo-specific, in fact. And we don't run into the problems that organic chemists do when we're talking biochemical reactions because of that enzyme mediation. So if we have this example, let's see if we can name that compound. It's cyclohexane, and which one is higher priority? It's the alcohol, right? So it'd be cyclohexane 1-ol, or just cyclohexanol, actually, and it would be 1, 2, 3, 3-methyl cyclohexanol. And we want to change that alcohol group to a better leaving group. All right, so we can conduct a reaction on that carbon attached to the leaving group. The problem is, under these conditions, when we treat this with concentrated hydrochloric acid, we get an SN1 reaction. Now, why is that? Well, hydroxyl is not necessarily a good leaving group, but if the carbocation is secondary, then hydroxyl becomes good enough to produce a carbocation, secondary carbocation on that cyclohexane ring. And then it can be attacked from either side by the chloride ion. So that's the basic problem with this particular reaction. Another possible side reaction has to do with rearrangements. If we treat the let's see, 1, 2, 3, 4. So we got a so that's butane 2-all. So it'd be 1, 2, 4, 3. It'd be 3-methyl butane 2-all. Okay, I'm practicing my nomenclature. If that undergoes an SN1 reaction, then it will produce a secondary carbocation with the hydroxyl leaving. That's an SN1, right? First step is leaving group. But it's more stable as a tertiary carbocation. So we're going to get a rearrangement, a carbocation rearrangement. And now the carbocation is on the tertiary carbon. And that's where the bromine attacks. And since this is not a chiral center, you're going to end up with just that single product. But it's not the product you want. Now, it's entirely possible that we could get a mixture. We could get some of the desired product, but we'd also have this side reaction that would produce an undesirable product. In other words, let's look at that first one. What could happen with that hydrochloric acid? Well, you could get a proton transfer to the hydroxyl and make a water molecule there as your leaving group. That would be a much better leaving group. Then the chloride could attack and produce a the stereoisomer you want. But then you have this side reaction that would produce stereoisomer that you don't want. Okay, that's what we're saying. We're not saying that this is the only reaction that can occur. This is a side reaction. So the reaction we want is an SN2 with the chloride product. But the SN1 is also there as well. And we can make a similar argument for the second reaction. So how do we get around that? Well, in this case, we're going to use a different reagent to attach a bromine to where the hydroxyl is. This is still a leaving group substitution or a transformation, a functional group transformation. So what we would really want is only one stereoisomer from as a product. Right? So one of the possibilities is to use this tribromo phosphorus reagent. And notice it's in aprotic solvent. Right? You don't want aprotic solvent because what would it do? Well, it would interfere by protonating that hydroxyl. And that would defeat the purpose of using the, actually, I should have said phosphorus tribromide. That's what it is. Phosphorus trichloride will do a similar thing. Okay, how does it do that? Well, it does not produce an intermediate carbocation, right? It's an SN2 reaction, so you don't get the intermediate carbocation as a side reaction. And you can do it under relatively mild conditions too. We don't produce any elimination products. In other words, no pi bonds are formed. And the conversion is stereospecific. So if you start off with the hydroxyl facing you, you're going to end up with a bromide, the bromine away from you. All right. So this is what the mechanism looks like. First, since you have all those bromines around that phosphorus, and bromines are more electronegative than the phosphorus, you're drawing electron density away from that phosphorus and making it electron poor. Whereas the hydroxyl group on your substrate is electron rich. So it attacks the phosphorus. And that's a nucleophilic substitution reaction, a bimolecular reaction, in which a bromine is kicked off of that phosphorus tribromide. And now we're attached to the former alcohol group with a phosphorus dibromide. Okay. That, as it turns out, is an excellent leaving group. Because why? Because it's very stable. Once it leaves, it's extremely stable. That makes a good leaving group. It's very much like water in that respect. And then, since it's a good leaving group, the bromine can attack the carbon, and now the leaving group can leave. And with the SN2 reaction, we're stereospecific. Right? The bromine can only attack from the backside. The bromine ion that's left behind can only attack from the backside because of the steric hindrance. So that's why you get an inversion of your stereocenter. And since it's SN2, we don't generate any carbocations. So we don't get a mixture. We get only one isomer out of this reaction. Okay. And you might have already guessed that there are limitations. The reason that this reaction works so well with the cyclohexanol is that the carbon that was being attacked in the SN2 step is an sp3 hybridized carbon. And we know that the sp3 hybridized carbon has the weakest bond, the weakest sigma bond with that oxygen. So it makes it's easier to break. Whereas if you have a phenol, right, this molecule is actually phenol, then that carbon is sp2 hybridized. And the sigma bond with the oxygen is too strong to break. So if you treat it with phosphorus trichloride or phosphorus tribromide, you're not going to get the halide formed. It will not happen. The other possibility, the other limitation, in fact, is that if you have that carbon surrounded by methyl groups, in addition to the oxygen, if that carbon is tertiary, then you're not going to get any product, or actually a poor yield, because of steric hindrance. All right, so those are two problems. Now let's look at this one in terms of what we can expect. We've got two hydroxyls here. Which one is the phosphorus tribromide going to attack? Well, actually, I should say it the other way around. Which one of those hydroxyls is going to attack the phosphorus? Well, what do we got here? Well, all the carbons are sp3 hybridized, so that's not an issue. But the hydroxyl on the left has a methyl group in the way. So you got steric hindrance. So that means the attack is going to come from the hydroxyl on the right. Okay. And when it does, it should produce the bromine is going to be substituted for the hydroxyl on the right. It would follow the same set of steps as we've seen before, but you won't get any, or you get, I suspect that you get minor products, right? Because steric hindrance doesn't negate the possibility of the reaction occurring. It's just a minor product. So the major product is going to be bromine on the right-hand carbon, and perhaps some bromine on the left-hand carbon, but not much. Okay. So suppose we have, we need to halogenate an alpha carbon that's next to a ketone or an aldehyde. In this case, it's next to a ketone. So how do we get that bromine on the alpha carbon? Well, we got to get rid of the alpha hydrogen and substitute for that the bromine. And it turns out that this reaction goes very well under basic conditions, right? Not acidic conditions, basic conditions. And here's the reason that basic conditions are required. With basic conditions, what we can do is proton transfer. The hydroxyl takes that alpha hydrogen, and now it produces an enolate anion. Which is resonating with, well, it's an enolate resonance. Let's just say that. It's easier to say. And that stabilizes it, stabilizes that molecule. Okay. But which one is a better nucleophile? Well, it turns out carbons are better nucleophiles than oxygens. And we make the comparison between, excuse me, the methylate anion versus the hydroxyl ion. It tends to be more nucleophilic. Okay, so even though the more stable compound is the one at the top in that resonance structure, and I would add this, right? When we say resonance, we actually don't have both of those structures. It's resonating between them. So the reality is that our structure is something in between those two. The actual structure is in that double barbed arrow somewhere. But as it turns out, even under those conditions, the oxygen is slightly negative and the carbon is slightly negative. And it turns out that the carbon anion, the carbanion, is more nucleophilic than is the oxygen. So it would attack the bromine, right? We just and this is elemental bromine. It attacks the bromine and frees up the bromide ion. And now we have, I think we would have no, this is not a stereocenter, right? Because you've got two methyl groups on there. So that's not stereospecific. But you would have that bromide ion out there. Oops, excuse me. Let's see. I was going to say something else. Oh, I think it's in a subsequent slide, right? Why does that carbanion attack the bromine? Because the carbanion is a nucleophile, but the dibromine molecule is just loaded with lone pairs. So why would it attack that dibromine? I mean, it's a nonpolar molecule, right? Okay. we're going to see in a subsequent slide that what we're doing is we're inducing polarity. So as that carbanion approaches the dibromine, it induces a polarity where one side is more positive than the other side. And that's why it will still attack the bromine. Right. We'll see that on a subsequent slide. I just wanted to make the point here because it just stood out. It was screaming to me to say something. Okay. So the good thing about halogenating an alpha carbon is that now it can serve as a substrate. It's got that bromine as a good leaving group, right? So it could, if we attack it with a nucleophile, we can replace the bromine with a nucleophile. Or if we attack it with a base, we can eliminate that bromine and form another, and form a pi bond, right? Now, trick question. When we attack it with a base and form an elimination product, why is the double bond on those two carbons there and not on the carbon that's attached to the oxygen? Why don't we form a pi bond over there? Like I said, it's a trick question. If we did that, how many bonds would be to that carbon? There'd be 5 bonds, right? That ain't going to happen. Okay. Just checking, reality check here. All right. Okay, so here's our induced polarity. And what we're saying is that the dibromine molecule is easily polarizable. And that's because the bromine atom itself is huge. This probably wouldn't be as effective with a dichlorine molecule because chlorine is a much smaller atom. So the dibromine would be a better choice. And it turns out that bromine's a better leaving group anyway because of its size. It can handle, stabilize a charge better than chlorine and infinitely better than fluorine because of its size. In fact, iodine might even be a better choice. Okay. So this is what alpha halogenation would do. But if, in this case, we're starting out with, excuse me, we still get the enolate, the stabilized enolate anion. But in this case, we're starting out with a stereocenter is our alpha carbon. Notice we got that big group on the left, and then we got an ethyl group on the right, and then we got our hydrogen, and then we got a methyl group. So that carbon is stereo specific, not stereo, it's a stereocenter. It's a chiral center. So we're going to get a mixture of stereoisomers. If we go back and look at the mechanism, or maybe we're going to get it on the next page. Let me see. The alpha carbon becomes a stereocenter with a mixture of RNS configurations. For this particular reaction type is going to produce a mixture. Let's see. No, I don't want to go there yet. I wanted to talk about the stereochemistry. So let's go back to the mechanism right here. So if one of those methyl groups on that bottom in the enolate anion, and the bottom one where the carbon has the negative charge, if one of those, so instead of 2 methyl groups, if we have a methyl and an ethyl group, Now that anion can be attacked from it can attach to the bromine from either the front or the back. We can produce a stereo center there with a mixture of R and S isomers. Okay, and the way it's presented there, we don't have that problem. But in this subsequent slide here, we do have that problem. If you want a mixture, fine. If you don't, then you got to find another way. Either that, you have a cleanup problem. Okay. So now let's go to the next. This could be a problem, or it could not be a problem. Under basic conditions, it's possible to not only brominate that alpha carbon once, but twice. So you could get a dibromine. That is, if you have two hydrogens in that location. And this is on the, for that molecule, it's on the left-hand side of the molecule. And notice that carbon, that secondary, the alpha carbon is secondary, which means it has a bond to two carbons, which means the other bonds are to hydrogens. So we've got those two hydrogens available. When we add a bromine, here's the problem. When you substitute a bromine for one of those hydrogens, that makes the other hydrogen even more acidic. And we're able to remove it with the hydroxyl anion in basic solution. Okay, so that makes it again available for substitution of another bromine. And it's all due to the fact that we're making that remaining hydrogen even more acidic. Okay, so the hydroxyl comes in there and we do another proton transfer. And now we've got another enolate anion that can further attack another bromine molecule, and we get a dibromine substitution. That may or may not be what you want. However, if we do this under acidic conditions, we only get a single substitution. So if you want a double substitution, do it under basic conditions. If you want a single substitution, do it under, acidic conditions. And these are mildly acidic conditions, I should add, based upon what we see there. What are the conditions? Well, you've got chlorine and you've got acetic acid. Okay, I'm remembering by convention, if we don't say dilute, then we mean concentrated, right? So this acetic acid is concentrated. So under these conditions, the second proton that's left behind becomes less acidic because the conditions are acidic already, and they tend to force the hydrogen to stay put. It doesn't want to leave. There's no incentive for that hydrogen to leave. And here's what it looks like in the mechanism. Under acidic conditions, actually, you're going to get a different reaction. Under acidic conditions, the carbonyl oxygen does a proton transfer from the acetic acid. And then we get another proton transfer, and they're only showing one proton there when the acetate ion attacks that proton on the alpha carbon. And let's see. I'm trying to establish whether we get, okay, what we're doing now is we're establishing a pi bond between the alpha carbon and the carbonyl carbon. And when that happens, 1, 2, 3, 4, it tries to, all right, it tries to make a double bond between the alpha carbon and the carbonyl carbon. And we can't do that unless we take the pi bond electrons from the carbonyl and put them on the oxygen. And then you only have 4 bonds with that carbon. So that will work. And it also produces an enol stabilization. And when it does that, it makes that secondary carbon into a carbanion. And now that can attack the chlorine. And when that happens, you only get 1 substitution. Because now you come in with an acetate anion and remove a proton from the carbonyl oxygen. And let's see. That's where the reaction stops. Right. That's where the reaction stops because now the carbonyl oxygen is being influenced by that chloride. It's a withdrawing effect of electron density away from the oxygen. So the oxygen now is not nucleophilic enough to for another proton transfer. Right. So that's where the reaction stops. Another explanation is given there. If it were to happen, you would have a positive oxygen. A formal charge on the oxygen would be positive and be less stable because of the withdrawing effect of the chlorine. All right, so the reaction stops there. We don't get a further proton transfer. So this, under acidic conditions, you get a much more complicated mechanism. Several steps rather than just a couple of steps for the basic situation. But as far as synthesis goes, you end up with a single substitution rather than a double halogen substitution. All right. That's as far as I got with my edits. So now I'm winging it. We're going to look at epoxides as substrates. Remember what an epoxide is? It's anything that has an oxygen in a trigonal group, a 3-membered ring. And you can have something out here, you can have something out there, but you've got this very strained 3-membered ring. And since it's very strained, it's not something that you can pull off the shelf. It's something that has to be made in situ. Now, if there are only 2 carbons and an oxygen, we call that oxyrain. This is known as an epoxide. Epi means upon, so the oxygen is upon the carbons. It's like a bridge between 2 carbons. That's not really a bridge. That's a misnomer. It forms a 3-membered ring with the oxygen. Now, what can we do with that? Well, the tendency for that 3-membered ring, since it's under such strain, is to open up. It wants to break one of those bonds on one side or the other and open up. And when it does, it's available for, it produces a carbon that's available for substitution. Okay. The overall synthetic procedure here is for example, that top one is bromoethane. And in aqueous, that doesn't make any sense. We got water and DMSO, so we've got a mixture. Water is a reactant. DMSO is the solvent. I can't explain why that is yet. At high temperature, and it takes a long time, 8 hours. And we're going to produce ethanol from bromoethane. So, I'm not sure why both of those are on the same page. They're like separate. All right. Maybe that top, we'll come back to that top one later. Let's focus on the bottom one. Under neutral conditions where you have sodium chloride and methanol, this oxy ring, the ring can open up and we can add a halogen, we can add the chlorine to one carbon, and the oxygen is protonated. So now we have 2-chloroethanol. Under basic conditions, we're going to produce, basic conditions and we've got a methoxy anion. So we're going to form an ether on one side and alcohol on the other side. Those are two separate reactions. We're not just saying one's neutral and one's basic with the same reagents. We're saying one is neutral because sodium chloride is neutral, and the other one's basic because sodium ethoxide is basic. Those are examples. So if we take that second one and we try to develop a mechanism for it, we find that one side or the other of that oxy ring can be attacked, right? The oxygen has a withdrawing effect. In addition to the bond strain that's imposed on that molecule, the oxygen has an electron withdrawing effect. So if the ethoxy it attacks the carbon from either side, then the bond is going to readily break. It won't have any problem breaking that bond. And that establishes a contact, a connection, a bond between the oxygen and the primary carbon. And then we've got an oxyanion sitting over there, and it's going to take a proton from methanol. So if we look at the previous slide, yes, methanol is the solvent and it's a reactant. It's a reagent. All right, so it gives up a proton and produces another methoxy anion. And that can go ahead and attack another one. So it's almost like a chain reaction. You keep producing methoxy anions. All right. So what can we say about did we define regiochemistry in chapter 9? I'm trying to think. I think we did talk about it a little bit. Regiochemistry references the symmetries that can come from a given reaction. So it's not just seeing the molecule sitting alone and talking about its possible isomers or naming it. We're talking about a reaction itself. Regiochemistry means these are the possibilities that can come out of a reaction. These particular isomers, or this particular, maybe just one isomer, we can specify from a given reaction. So we can have neutral conditions or basic conditions. So let's see, what kind of conditions do we have here? Well, we're given this a two-step reaction, right? We're adding an ethoxy anion, and what that should do is produce let's see, those are going to be basic conditions. The first one's basic conditions, the second one's acidic conditions. So we're going to produce an asymmetric ether with an alcohol. I consider the second step something of like a cleanup. We call it a cleanup step, right? We get a desired reaction with the first step, but we're not all the way there, right? It's basic to start with, then we acidify it to get where we're going. And I think the next slide should show us the mechanism. Right, so with that ethoxy anion attacks a carbon, and we have okay, in this case we have methyl groups. Okay, we got methyl groups, so we have two stereocenters. We've got one stereocenter. Possible chiral centers. All right, we do have two possible chiral centers. Now, which side is going to get attacked first? Well, steric hindrance tells me that the left-hand side of that epoxide is going to be attacked first. It's less hindered. So we're going to attack that carbon and open up the ring. And now the proton transfer occurs. And that during the second step. The first step produces the charged oxyanion. And then we acidify it with sulfuric acid, and we get a proton transfer. And that's what I would call the cleanup step. And that would guarantee now that we have, now, why do we need that cleanup step? That's my question. The first step is definitely steric hindrance that says the left-hand carbon is going to be attacked. So let's see. Have we talked about the Walden inversion yet? It seems like we had that umbrella turn inside out. Yeah. When we were attacking from the back side or the front side, it inverted. Okay. But notice that now the carbon attached to that oxyanion is a tertiary carbon. And the oxygen is going to want to tend to stay an anion. So we have to treat it with acid to protonate that oxygen. Otherwise, we end up with a charged species in basic solution, and we don't get the final product, the alcohol, out of it. So we have to, the second step has to be a proton transfer, and we have to force that proton transfer. Whereas if it were a primary carbon, then the proton transfer would happen automatically. All right. So what can we expect from this reaction? It looks similar to the one we just did, wouldn't it? Predict the major product in the following reaction. Okay. So what's the nucleophile? Nucleophile is going to be the ethoxide ion, right? Which carbon atom of the ring is attacked? Let's see, dimethyloxymerine 2,3,2-ethyl 2,3-dimethyl. So which is the number one? 2,3-dimethyl. Okay. Oh, I didn't see that. This is different. Hold on a second. Let's back up. Yeah, no, it's the same. I was blinded by that wedge sticking out, and I didn't see the extra carbon on it. So that carbon on the right of the oxyrane has a methyl and an ethyl group on it. Okay. Um, so are we calling oxygen the number one? Right? Because we've got a 2-ethyl and then we got a 2,3-dimethyl oxyrane. Okay, I think that's what's happening. The oxygen is given the number one position. I haven't seen that before. Okay, well, set that aside now. The nucleophile is the ethoxy anion, and it's going to attack the less sterically hindered carbon of the oxyrane. And then the remaining substituents are attached to the carbon that's attacked. They have to flip upward after the ring is opened. And then we have to protonate that oxygen. So we're going to attack the left-hand side, and that's where the ether is going to form. And the oxygen is going to switch over to the side with the methyl and the ethyl group on it. Okay, and then we have to protonate that one. So this is what it looks like as a mechanism. Right, we're attacking the left-hand carbon. That opens the ring, produces the oxyanion, and then we need the acidic, right? That's a hydronium ion there on the arrow. We have to attack that, remove a hydrogen, and that produces the alcohol plus water. So as this reaction proceeds, I would expect the acid concentration to decrease. Wouldn't you? Because we're using up the hydroniums. Now, if it's concentrated enough, we probably won't notice it. Right? You probably couldn't measure it with a pH meter. But in fact, we should see less acid in solution as it proceeds. Okay. So what would happen? Let's see. We reacted with the oxyanion. Right? Now what would happen if we just have a purely acidic solution, an aqueous solution with a strong acid, hydrobromic acid? What's going to happen? The nucleophilic attack is at the more highly alkyl substituted carbon. Right? So the carbon with that methyl group on it is going to be the one that's attacked by the bromine under acidic conditions. Here's the mechanism that tries to explain it. Okay, what's happening is we get a proton transfer to the oxygen, and that starts to partially break the bonds. And the weaker bond, when we transfer that proton to the oxygen, it makes the oxygen slightly positive. And the bond weakens more with the secondary carbon than with the primary carbon. And that's the one that the bromine then attacks because the bond is weaker there. And because it's weaker, it becomes more positive. All right. A fast proton transfer occurs, generating an intermediate with a positive charge on the oxygen atom in the ring. Okay, we see that. We delocalize the positive charge on the protonated oxygen. Both carbon-oxygen bonds partially break in the intermediate indicated by the dash bonds, but we're saying that the primary oxygen-carbon bond is stronger. Why is that? All right, both carbons gain a partial positive charge. The additional alkyl group on that carbon on the right makes the positive charge more stable at that point. Stabilizes the developing charge on that secondary carbon rather than on the primary carbon. And that makes sense. It's not a full carbocation, but the positive charge is more stable. Right? So the break is favored on the more substituted carbon. It accommodates more of the positive charge on the secondary carbon than on the primary. And that's where the bromine attacks. The bromine ion then attacks there. So that's hopefully is an explanation why the more substituted carbon is the one where the bromine attacks. Okay. Okay, further explanation. All right. In the beginning, the bond distance between the oxygen and the two carbons is the same. Well, yeah. And then when we protonate the oxygen, they actually measure that the bond to the more substituted carbon is the longer bond, which means it's weaker. Longer bond means a weaker bond. Okay. All right. Now, we just assumed at this point that we had the oxyrain, like we just pulled it off the shelf. But in fact, those epoxides have to be formed in situ. I can't think of a single, well, perhaps the more substituted epoxides could exist, right? They would be more stabilized, but they wouldn't last very long, I don't think. So the epoxides are extremely valuable for conducting nucleophilic substitutions. How do we form them? One way is from the halohydrin. The halohydrin is we've got two adjacent carbons. One has an hydroxyl group on it, the other one has a halogen on it. If that's the case, and we treat them with a strong base, with an aprotic solvent, and it takes a while, 24 hours, to form your epoxide. So you probably have to set it up and let it cook for a whole day before you can continue with using it from that point on. And you end up with an efficient production of an epoxide. So the mechanism is given below. So since this is under basic conditions, you've got a strong base there, the hydroxyl. It's attacking the hydrogen attached to the oxygen because that bond is weaker. Right? The oxygen has a withdrawing effect. So it makes that hydrogen more acidic. And the hydroxyl takes the proton, and now we have an oxyanion. And it attacks the more electrophilic carbon attached to the chlorine. Because the chlorine has an electron withdrawing effect, it makes that primary carbon, it makes the primary carbon available for an intramolecular reaction. Right, so here we have another example of an intramolecular reaction we were introduced to in chapter 9. This is another example. And I think the reason it takes so long for this to happen is because because of the bond strain. Right? It takes a while for that reaction to occur. Okay. So that was one way to form the, I'm not sure, that just gives one example for a primary epoxide. How would you get a secondary epoxide out of that? Would it be possible? if we put the chlorine, instead of on that primary carbon, if we put it over to the left on that secondary carbon, could you still get an epoxide now with a methyl group on one side and a ethyl group on the other side? I'm not sure. I'm not a synthetic organic chemist, so I can't say whether that would happen. It's an interesting problem. Okay. The reactant here, one of the reagents is diazomethane. And what we're doing is we're treating this carboxylic acid with diazomethane to yield a methyl ester. So how does that happen? We have to do it in aprotic solution with ethyl ether, right? That ET2O is ethyl ether. And then we also have methyl chloride, dichloromethane. So here's what we're going to see. Remember, triple bonded parts of a molecule. In this case, they're nitrogens. It could be carbons in some other situation. But in this case, the presence of those pi bonded electrons cause the molecule, well, actually, it's a resonance structure. We're resonating between a negative carbon and a negative nitrogen, and that tends to stabilize it. But the reacting species is the one that where the electron rich is on the carbon. And with that, we can proton transfer off of this acid. Now that's fairly easy, right? Because we've already made that hydrogen on the carboxylic acid is very acidic by comparison, because we've got two oxygens there, and they're making that hydrogen very acidic, so the transfer is easy. I suspect it's a very fast transfer, proton transfer, and actually it looks like it's an equilibrium situation. And then once you get the deprotonated carboxylic acid, it now can go attack the carbon on the diazomethane and break that bond, and that will form a bond between the oxygen and the methyl group, and that is the methyl ester. In fact, we used to use this reaction when we were analyzing sample extracts, the plant sample extracts for their acid composition. We wanted to use a gas chromatography. And for gas chromatography, your analytes must be volatile. You got to be able to turn them into a gas easily, right? They have to have very low boiling point. Acids have a very high boiling point, so we couldn't put the acids directly into the gas chromatograph and expect to get anything out of it. They would stick to the stationary phase and stay there. So we would do this procedure. We would add sample into a glass vial, an ampule, and then we would add diazomethane to it, and then we would seal it just with a flame, seal the end, and then put it in the oven for overnight to get that reaction to go. And then the next day, we would, once you open it, the nitrogen gas is going to be blown off. And the diazomethane produces a peak of its own, so we can just shoot it directly into the gas chromatograph, and the diazomethane will come out as its own peak, and the other peaks would be the the methyl esters of our various carboxylic acids. And we could get a profile from those the different amounts of the carboxylic acids by using gas chromatography. About amines and quaternary ammonium salts from the halides. We're still talking about functional groups and their transformations. Well, this is just a reminder. What a primary amine is, it's got one allyl group on the nitrogen, secondary has 2, tertiary has 3, quaternary has 4, and it's charged. It has to be charged. That's the only way it can happen. So quaternary ammonium compounds are very good cleaning products. Right? I may have said this before. If you check out bottles of cleaning products in the store, if they're ammonia-based, you can still get ammonia off the shelf, of course. But the safer ones, and just as effective as ammonia, are the quaternary ammonium compounds. These are different examples of amines, right? Amino acid, everybody knows that one. Histamine, it's another, let's see, histamine. Oh, okay. Histamine's what causes you to itch, right? Causes allergic reactions. So you take Benadryl, and that's antihistamine. So it suppresses the function. Histamines on a tissue level, what they do is they cause the capillaries to open up, and they let fluids flow out into the tissues to mitigate tissue damage. You know, to get the white blood cells out there for infections and so forth. But with too much histamine, they can cause tissue damage, right? So your body has a mechanism for limiting that, and sometimes it doesn't go far enough, and that's when we take Benadryl. Methyl orange, right? It's another type of amine. Right? Methyl orange is a dye that we use in titration chemistries. Phenylephrine, decongestant. Right? It's great for decongesting, but it also has a rebound effect. If you squirt some of that up your nose, it'll open your passages, but by morning you're going to be stuffed up again. And it also affects your blood pressure because it is, as a decongestant, what it does is it constricts, it's a vasoconstrictor. Right? So it reduces the ability of the vessels to deliver fluid to your nasal passages, for instance. But if it's systemic, once it gets into your system, it does the same thing for all your other vessels, and that increases your blood pressure. So if you're susceptible to, if you have high blood pressure, then you want to limit your exposure to these decongestants. Pseudoephedrine, you can still get it, but it's regulated. In other words, you got to go to the pharmacist to get it for one simple reason. It's very easily converted into, my mind just went blank, methamphetamine. So phenylephrine does a fairly good job. It's not as good as pseudoephedrine, but it's reasonably good, and it can't be easily converted into methamphetamine. Is that it? No, there's more. Let me see. Let me just check my hard copy and see how far along we are. We should be getting close. How'd that page get printed upside down? And that one too. Yeah, we're what, a half a dozen slides away or so. Okay. Nucleophilic substitutions. Again, this time we're going to alkylate ammonia and amines. So I think that was the purpose of reminding us what an amine looks like. And we can form, actually we can, in these mechanistic steps, we can take an alkyl bromide and substitute the ammonia for the bromine and make an amine out of it. So the primary amine is possible under these conditions, where the bromine, we only substitute one alkyl group, excuse me, on the amine. That makes a primary amine. But I suspect that it's going to continue. Right? So we've still got a lone pair of electrons on that amine, and it's going to attack another alkyl group. Bromine leaves. Now we have a positively charged, a positive formal charge on a secondary amine, and the ammonia removes the hydrogen, and the electrons that were attached to that hydrogen now are transferred to, one of those hydrogens is transferred to the nitrogen. So now we're neutral again. And we can go ahead and proceed to another amination. So what you're going to get from this situation is you're going to get a mixture of primary, secondary, tertiary, and a trace amount of quaternary amines. Now, I think the reason that most of it's going to be primary, fewer secondary, and we're getting into steric hindrance now. So as the steric hindrance increases, you get less and less of the more substituted amines. If you make sure that you have a very large excess of the alkyl halide, then you can increase the amount of the quaternary ammonium product. You also have to increase the temperature. So there's your synthetic solution to the problem. If you want a quaternary substituted amine, then you've got to increase the temperature, increase the substrate concentration, and weight. All right. Elimination. We've been talking about substitution reactions up to this point. With elimination reactions have been side reactions, problem reactions. Now, what if you want a, what if you want an elimination to produce an alkene, or an alkyne for that matter? This particular reaction is the Hofmann elimination reaction. And it's going to be a three-step process. You got methyl iodide in large excess, followed by silver oxide, and then you heat it after that. Okay, those are the three steps in this procedure that get you to where you want to go. And the major product of this Hofmann elimination is anti-Zaitsev product. So remember the Zaitsev products produce the more substituted alkene. So the Zaitsev would have produced a but-2-ene. The anti-Zaitsev produces the but-1-ene. And under these conditions, that's what you get. All right, here's the mechanism. So we've got that methyl iodide that's going to be, actually the methyl iodide is the substrate and the amine is the attacking group. And now, how did I know that was going to happen? I should have known it was going to happen because iodine is a good leaving group, right? And it would make the carbon slightly positive. And the amine has the lone pair available to attack the carbon. So once we've eliminated the iodide and attached the methyl group, now we want a proton transfer. And a proton transfer then stabilizes that amine. And the second step, now we're going to add, let's go back. I think the second step, we're going to continue alkylations. Yeah. If we have an excess, yeah, an excess in of the methyl iodide, then we're going to continue alkylations to produce the quaternary ammonium compound. Next thing we want to do is treat it with silver oxide. And let's see, did they add base in there? It doesn't say base. Right. So how does it replace iodine with hydroxyl? I don't know, because that wasn't listed in the synthetic steps. So as it turns out, the tertiary ammonium substituted compound is going to be very stable. It's a good leaving group. So now, once we have oh. Okay, so there's a reaction that's not explained there. The iodine reacts with the silver oxide and releases hydroxyls. That's where we get the hydroxyls. Now, why did we do it that way? Because we didn't want to use a strong base in itself. We wanted to remove the iodide so they would not be an issue. And reacting iodide with silver oxide produces the hydroxyls. Excuse me. And then the hydroxyl can attack the primary hydrogen. And the reason it does that, this anti-Zaitsev, normally it would have attacked the number 3 position, wouldn't it? That would be the Zaitsev. The anti-Zaitsev, why did it do that? Why did it attack the primary hydrogen? Probably because of steric hindrance. Yeah. The primary hydrogen is more acidic. No, that's why it did it. The hydroxide attacked the primary hydrogen because it's more acidic. With the quaternary ammonium compound as withdrawing electron density, it draws more electron density away from the primary hydrogen than it does from the number 3 position. So now we get the elimination reaction, and the tertiary amine is a good leaving group. So this is, we're still Hoffman elimination, and this is regioselectivity. All right, so we're going back to the point where we've got that quaternary ammonium compound, and we're looking at, we're using a Newman projection. And we're looking down the 2,3 carbon axis. Okay. The 2,3 carbon axis, if we rotate that around to the gauche position where the methyl groups, one of the methyl groups is on the number 3 carbon is hindering the amine, then it tends to shift to the anti configuration, which is more stable. But in those conditions, the E2 reaction is not favored because both of the hydrogens that would need to be eliminated are now occluded by the amine. So the other possibility is for the is looking down the 1,2. We do the Newman projection down the 1,2 axis instead. Now we get the leaving group is now anti to the hydrogen, to the hydrogen that can be attacked, and that's why it's anti-Zaitsev. In the secondary, in the E2 reaction is now favored in the bottom situation. Does that make any sense? It sort of makes sense to me. Remember, the elimination is preferred. The E2 elimination is preferred for the anti-hydrogen. And the only way we can get an anti-hydrogen out of this is to go to the number 1 carbon. That's why you're going to get a double bond between 1 and 2 rather than 2 and 3. Because the more stable, on the top one, the more stable orientation doesn't put the hydrogen in the anti-position. Right, so that hydrogen on that carbon won't work. Okay, enough of that foolishness. So how do we generate alkynes by elimination reactions? And these are examples of alkynes. Naturally occurring pesticide. I don't know that one. Carinol and norethanodrel. This is used to be an oral contraceptive. There must have been some side effects, and they don't use it anymore. Okay, hold on a second. Generating alkynes by elimination reaction. All right, we're not generating an alkyne here, except insofar as we're forming a carbon, we're changing the carbon skeleton. So what we want to do, first thing we want to do is make an anion. So we treat the primary alkyne, which has a hydrogen on the end, treat it with sodium hydride to remove that hydrogen, right? And again, this is going to produce hydrogen gas. And once we get that anion, we can attack an alkyl bromide and form a carbon-carbon bond. All right, so we can add an alkyne by eliminating the bromine. So this is not really an elimination reaction. No, this is a substitution. Come on. Okay. The terminal alkyne is weakly acidic, all right? We can deprotonate it with the strong base, and that's where the sodium hydride comes in. Then we produce the strong nucleophile, all right? That's good. And we can get an SN2 substitution reaction out of it. Okay. Then the alkyne can undergo functional group conversions to produce other types of compounds, alkenes, ketones, aldehydes. Okay, so this is like a first step in a sequence that's going to produce other types of functional groups. And I think the alkynes are good candidates for that because they have those pi-bonded electrons, which are more loosely bound. And they lend themselves to functional group transformations. So a lot of your reactions are going to start with alkynes in order to synthesize the different types of functional groups. Okay, this is a terminology here. The leaving group is vanillic. In other words, it's attached to the double bonded carbon, but it's opposite the the hydrogen that's being attacked, and that can produce your alkyne. So this actually is how you synthesize an alkyne. Now that R group, the right-hand R group on the first reagent, I assume it can be anything. And I wouldn't be surprised if you could, well, if you made that hydrogen, then it might, no, it wouldn't attack that hydrogen because that's the same one the leaving group is on. And that's how you produce your alkyne. Um, so these substrates are resistant to nucleophilic substitution and elimination reactions. So how do we get it to go? That's the question. Extreme conditions are required. High temperatures, 200 degrees Celsius. That's a pretty high reaction condition. All right, so here are possibilities. We can see where the chlorine is. That's going to be the good leaving group, rather than the bromine on the benzyl group, because you can't get anything out of that one, right? You can't produce a triple bond on a benzene ring. Just it doesn't work. You have too many bonds left over for the carbons. So this selectively causes the alkyne to be formed in between the phenyl rings. Then what? Oh, the second one produces a double alkyne. We're going to talk about it later in terms of conjugation, conjugated bonds, double bonds. I wonder if this double alkyne is also stable because it's conjugated. I wouldn't be surprised. And we'll have to define what conjugation means later. But it's a stabilizing effect. Okay. So if a much stronger base is used, such as sodium hydride or sodium amide, the elimination can take place without extreme temperatures. But I think the sodium hydride and the sodium amide are more difficult to work with. Safety-wise, that is. How do you form a terminal alkyne? A terminal alkyne is one that's it's on the number 1 and number 2 carbons. So you need a very strong base in an aprotic solution. And whereas I had a terminal workup for a previous synthesis, this is a preliminary, a first stage workup. Oh, no, it isn't. It's the second stage. What am I doing? Requires an acid workup. Okay. So we must have a charged species that has to be neutralized some way. Oh, I see. We've got an environment with strong base, and it's going to leave a charged alkyne, and we can't have that. All right. So the mechanism, I think, is on the next slide. All right. So we can produce a terminal alkyne with that good bromine leaving group, but then the base is going to pluck a hydrogen, is going to proton transfer off of that alkyne and leave it charged. So what we have to do now is add a quaternary amine. Yeah, let's see, acid workup, ammonium chloride. There's our quaternary amine in aqueous solution. So we go from aprotic to protic with an acid. Actually, the ammonium ion, yeah, it's an acid, right? Ammonia is a base, so its conjugate acid is ammonium. So that makes a hydrogen available and produces ammonia. So I bet when you do that acid workup, you're going to smell some stuff. You better do it under a hood, unless you want to get blown over by ammonia fumes. All right. These are other examples of alkyne formations. It looks like these are all primary alkynes. This 1,1-dichloropentane looks like it eliminated one chlorine to make a double bond and then another chlorine to make the triple bond. Yeah, that's what happened. And similarly with this 1,2-dibromo-1-phenylethane, you eliminated one bromine to make the double bond and another bromine to make the triple bond. Now, why are the chlorines on the same carbon and the bromines are on different carbons? Probably has something to do with that phenyl group. Oh, and it's not showing us a mechanism. It's just showing it examples. Right? So that's it.